I like to think of this first session here as it's really the mathematics and science section, so pretty cool stuff. So our first speaker today is Lloyd Goldstein. He's a computer science major and has quite a few minors in economics, sociology, and statistics. Today he's going to be talking about a project that he did with Dr. John Kettering, who is a fellow in RISE, our sort of resident statistician. And he'll be talking about reductionist statistics and the crisis of reproducibility, pretty serious stuff, issues in modern research practices. So join me in welcoming Lloyd.
Hi, everybody. I'm Lloyd, and Dr. Hendricks was very kind and saved me the trouble of reading the entire title. It sounds wordy. We'll get to it. It'll make sense, I promise. So, quick roadmap of what we're talking about. First, you're going to get a really short crash course in the statistics that you will need to know to kind of understand the problems that are going on here. I'm going to talk about the problems. It's going to make you all very sad. And then I'm going to talk about some potential solutions, and we can be a little happier. So, first, very quick crash course in hypothesis testing and p-values. So basically, hypothesis testing is a mathematical mechanism we can use to test a hypothesis or a theory we have about a certain population. So we can take a sample of data from that population and do some math on it. That's not important, we're not going to get into it, to get something called a p-value, which can be defined as the probability that a test statistic, at least as significant as the one observed, would be obtained, assuming that the null hypothesis was true. So the null hypothesis in this case is basically the statement that the differences in the sample data from our our expected population data are due entirely to random chance, and that there's not actually a meaningful difference between the sample and what we think the population is. And this definition of a p-value is very wordy, but every word is important, and yes. So often, you might ask, what's a good p-value? So oftentimes we use a threshold of p is less than 0.05, which would indicate a 5% chance, as a threshold for what we call statistical significance. And that was a lot of words, so we're going to do an example to make it make a little more sense. So we want to know whether the students at a certain high school have an average IQ that is higher than the nationwide average. So I made up some example data. We've taken a sample of 30 students. They have an average IQ of 104, and we're working off of the commonly accepted belief that the average IQ nationwide is 100 with a standard deviation of 15. We're going to do some math. We're going to get a p-value of 0.07. 0.07 is not, in fact, less than 0.05. So first of all, this does not prove or disprove anything, but we can say that we do not have evidence suggesting that the students at this high school have an average IQ that is higher than the nationwide average IQ, of course, using the p is less than 0.05 cutoff rule. Some people use p is less than 0.10, in which case we would have statistical significance. And so this all sounds very nice, but there are some problems when we don't be very careful. First, before I start ripping into current research practices, I should emphasize that people that do this research are not bad people. They're not unintelligent. They're not trying to be bad at statistics. They are not trying to lead us astray. They're under a lot of pressure to get results that are publishable. Their livelihood basically depends on, in some cases can depend on p is less than 0.05, and the solution is not just telling these researchers that they are bad people. Like, that's not what we're going for here. So, but it is the case that having a statistically significant p-value in some fields and in some time periods, like recently, is enough to make research publishable. And the problem with this is that we're not looking at our data in context, and we're losing information. So when p-values were originally kind of brought about, they were intended to be an indicator of whether we should look more closely at the data, not be an end unto themselves. So we started using these like a filter, where we put a bunch of information into this convenient statistical wizardry filter thing, and at the other side pops one convenient value. So, as an example, with our example that we looked at, we've got a bunch of information here, right? We've got a sample size of 30, a sample mean of 104, a population mean of 100, a standard deviation of 15, and these are all things that we could look at and think about, but instead we're putting them all into a filter and we're just saying, okay, P is 0.07, and we're just moving on. And sometimes that's not the best thing to do. So let's take a closer look at our example, right? So first, I said we have a sample of 30 students. We don't know who those 30 students are. We could have taken IQ tests of the 30 students with the highest GPA in the school, so we got the 30 students with the highest IQ. That's not representative of the entire population. We could have gotten the 30 students that came to lunch first, so we could have sampled the 30 hungriest students. That's not representative of the entire population. We also don't know how many students are at the school. If there's 100 students, a sample of 30 is probably fine. If there's 4,000 students, we need a bigger sample. And so I said we're working off the assumption that population mean is 100. We don't actually know that to be the case. And with IQ, it's kind of a commonly held belief, but I doubt it would hold up if we actually IQ tested every single person in the country. And then I said we don't have statistical significance because 0.07 is greater than 0.05. 0.07 is really close to 0.05, and the fact that our p-value is 0.07 might disqualify this from being like a publishable result or something doesn't really make a whole lot of sense since we're talking about a 2% difference. And you'll notice that I made the sample mean 104, which seems kind of arbitrary. If the sample mean was 105, the p-value drops to 0.03 and suddenly we have statistical significance. So think about that, like a difference in 1 point in sample mean IQ can take this from non-publishable to publishable in some fields, in some circumstances, which seems not really good. So I've talked a lot about, I've mentioned the word reproducibility a few times. I haven't actually said what it means, but one of the core tenets of kind of the scientific method and how science is supposed to work is for a discovery of anything really to be accepted, it needs to be reproducible by other scientists in other scenarios. But our current somewhat poor research method practices have caused this to start to slip, and this is something that people are aware of. So one of the most prominent science journals called Science published an editorial in 2014 calling for better statistical practices, and in 2018 a guy named Andrew Gelman wrote an article about it that appeared in the New York Times. So prominent news outlets are aware that this is actually a thing. So we've been sad, now we're gonna be happy. Here's some, so a lot of prominent scientists have started, they're aware of this and they're working on possible solutions. And one thing that has been proposed, most notably by John Ioannidis, is lowering the p-value threshold from 0.05 to 0.005, which would probably help get less kind of fraudulent results, but isn't really attacking the root of the problem. Encouraging researchers to work together and share data could be very helpful because researchers are notoriously afraid of other people, beating them to their publication, and so they're reluctant to share data. And that's not any one of their individual faults, but changing the ethos of the research community is something that would be really difficult, but also really helpful. But I think kind of where it all comes down to is how we teach statistics. And again, I'm not trying to indict statistics professors, I'm not trying to indict statistics teachers. I would not be here if not for all of my wonderful statistics professors, and I'm not trying to say that statistics professors are bad. But that said, we need to do a better job of teaching our students to think in context and in context of their data and think about the process more than the solution. The solution looks nice, but the process is more important. So the ASA, the American Statistical Association, the American Statistical Association, in 2019, actually literally a month and a half ago in February, they published an issue of their magazine dedicated to basically solving these problems and pushing for better statistical research practices. And the centerpiece was an editorial called Moving to a World Beyond 0.05. So kind of working towards a research community where we use things other than just the statistical significance threshold of 0.05 to determine whether we have a result. And you may have noticed that I spent a lot of this talking about things that are bad, and that was not really my intention, but there are a lot of things that we can do also in our research that would be good. And the ASA proposed the atom concept in this February 2019 issue, which stands for, accept uncertainty, be thoughtful, be open, and be modest. And basically what it boils down to is accepting that you are not always right. You cannot always explain everything in your data. Sometimes there will be patterns that you cannot necessarily explain, and that is okay, and it is okay to accept that. And so in conclusion, this is a real thing that is happening in the research community. I haven't, kind of emphasized that enough or something. But we're starting to make strides towards making it better. The academic community is taking note of these issues. We still have a long way to go. And again, I want to emphasize that as we teach and as we learn statistics, I think probably the most important way to fix this issue is that we need to think about the process. We need to be encouraged to think about the process more than the solution. And I mean, there are plenty of students in here that are doing research, have done research, will do research, whatever. And that means that the solution to this problem comes from all of us, right? Like when we do research, we can't just plug our data into a chi-square test and say, okay, p is less than 0.05, we're good to go. We need to think more about the context of our data. This means that the solution starts right here, right now, with us. Any questions?
So I think we have time for one or two questions.